Hello everyone, welcome back to the channel. So today we're gonna do a video where I actually cover all the calculation questions from October-November 2025 paper 1-4, except the uncertainty question, because I think the uncertainty calculation questions you all should be fine with it. I'll cover other than that. So this is gonna be a really long video. Therefore, what I plan to do is to cut the video into parts so that the video is not too long, because I know some of you have a really short attention span. So I'm not going to make it too long. I'm going to make it short and nice and put it into parts so that you can watch it and do it on your own as well. So without further ado, let's get to it. But before we start, just to let you know, the questions probably are not in order. It's like 17, 12, 6, 10, then after that it's gonna be in order. So just bear with me, okay? Because I was trying different questions. And yeah, so now let's get started. Okay. Question 17. Anyway, this is from paper 1-4, okay? Just in case you didn't get it the first time around. It's October-November 2025, paper 1-4. Okay. Starting with question 17. A toy car travels around a vertical loop track. Okay. The toy car is released from rest at a height of 58 cm. From rest, okay, above the bottom of the vertical loop. The car is at a height of 32 cm when it is at the top of the vertical loop. So this is basically the vertical loop, okay. Assume that no resistive force act on the car. Wow, this is so nice, because you don't have to consider work done against friction. What is the speed of the car at the top of the vertical loop? So what is the speed at here? Okay, so what we can do is we can separate the energy into two sections, which is initial energy and final energy at this point, which is initially is at the starting point, final is at the top of the vertical loop. Okay, now let's see what energy is present at the initial point. We have GPE, of course. Okay, do we have kinetic energy? KE? No, because it says it released from rest, so we don't have kinetic energy. Now let's see at the final point. Do we have kinetic energy? Yes, of course, because they're asking us to find the speed. That means there is a kinetic energy. Unless somewhere in the answer has 0, then probably no, which will not happen. They will not give you 0 meter per second as an answer, by the way. Then moving on, do we have GPE, which is gravitational potential energy? Yes, we do, but it's probably lesser than the initial one, because initially it was at 58 centimeter. Now it's at 32 centimeter. Okay, check the unit, it's in centimeter. Later when you are calculating, make sure to change it to meter. Very important. Okay, now let's do our equation. Initial energy equals to final energy. Okay, it's equal because we know that energy transfer is not destroyable. What can't be destroyed? Energy can't be destroyed. What did I just say? Energy can't be destroyed. Conclusion is energy can't be destroyed. So whatever initial energy there was, it has to be equal to the final energy. Okay. Not destroyable. Okay. Anyways, grammatically I'm not sure if that's correct, but yeah. Initial energy, we say there's no kinetic energy, so only gravitational potential energy, which leaves you with mgh. I'm going to put hi to show the initial height. Okay. Final, we have both kinetic and gravitational potential energy. So this is final velocity, final height. Okay. M all cancels out, which makes sense because they didn't even give you the mass of the car. G, I'm just going to leave it as a constant as itself. Initial height is 58 times 10 to the power of -2 equals to half. VF squared is what we are finding, plus GHF is 32 times 10 to the power of -2. Okay, now Let me bring all this G to one side. Wait. Equals to half VF squared. I just realized that, okay, no, I thought my calculator was not with me. Okay, I found my calculator. Anyways, so put this in your calculator. You should get, okay, 9.81, okay, 2.5506 equals to half VF square. VF square is times 2. 5.1012 VF is square root of your answer. You will get 2.26 meter per second. Round these dots to two significant figures, it will give you 2.3 meter per second. Okay, so before I end, I just want to say that it's not necessary for you to do this step by step. If you can mathematically compute this, you can just do it, because this is paper 1. It's not paper 2, so you don't have to do it step by step. If you can go from here to here, that would be great. You can save a lot of time. I'm just showing you step by step here. Okay, and your answer is 2.3 meter per second. Your answer is B. Yeah. Alright, so that's question 17. Basically, you identify what energies are present initially and what energies are present at the final point. Equate them, because energy can't be destroyed, so they have to somehow transfer from initial to final. Then do some algebra, you should get your answer. Don't forget to square. It's a very common mistake, so don't forget to square. Okay. Right, so that is question 17. Let's move on to question 12. Okay. The diagram shows a stationary sphere that is just fully submerged in a liquid. The radius of the sphere is R. Radius of the sphere is R. And the density of the liquid is P. The acceleration of free fall is G. The air exerts pressure PA on the surface of the liquid. Okay. What is the pressure at the lowest point of the sphere? Okay, they're asking at this point. And given that the air exerts a pressure of PA. So this is basically atmospheric pressure. Okay. So to know what is the pressure at this point, right? Basically, we need to know what is the pressure of the liquid acting on the sphere at this point. So to know that, we know we have a pressure formula, P equals to rho G H. Why does my rho look like that? Wait. Rho G H. It still doesn't look nice. Okay, anyway, it doesn't matter. So given you have rho here, okay, G is just a constant, rho and G, they just give you as rho and G. Now, what is your height at this point? You know the radius is R. Right, this whole thing from here to here to the end point, which is the not showing the end point, lowest point, it's 2R. Because you're finding the pressure at this point, am I right? So to know the pressure of liquid acting on the sphere at this point, the height, or you can say the depth at this point, is 2R from the surface. So this should be 2R. Basically, it's 2R rho G. Now, to know the total pressure, okay, just going to put as P total. It's atmospheric pressure. You must add your atmospheric pressure plus the pressure at this lowest point. This is 2RP. Not P, rho. Oopsie. Rho G. This is your final answer. You must add, because at this point you have the atmospheric pressure acting on you this way, and you have a pressure at this point. Pressure of what? Pressure of the liquid on, pressure of the liquid on the sphere at this lowest point at the depth of 2r, or height of 2r from the surface. So your answer should be C. Okay, yes. So don't get confused by these volumes and you'll be thinking, oh my god, I need to use volume. So I say, do not look at your answers, okay? Do the question based on your understanding. Then you look at the answer. You don't look at the answer, then you do the question. Because the moment you look at the answer, you see volume, oh my god, I need to use volume, you'll get confused. You'll get drifted away from your understanding. So look at the question, do the question first, then you look at your answers. Okay. Alright, next is question 6. So you're basically jumping around. Yeah, we went from 12 to 6. Okay. An aircraft on a runway accelerates uniformly from rest to its takeoff speed of 58 meters per second. The acceleration of the aircraft is 4.2 meters per second. And the aircraft uses 74% of the length of the runway. Let me highlight first. From rest, accelerates uniformly. That means you can use your kinematics equation. From rest to its takeoff speed of 58 meters per second. Acceleration of the aircraft is 4.2, and the aircraft uses 74% of the length of the runway to reach its takeoff speed. What is the length of the runway? Okay, so when you have kinematics question, it's always very good to list down what information you have. Then you will be able to find out which equation to use to find the answer to this question. Okay, we have U, initial speed is 0 because it was at rest. Takeoff speed, which is the final speed, is 58 meters per second. Acceleration is 4.2 meters per second square. And the aircraft uses 74% of the length of the runway. So I'm going to label the length of runway. Did I just say runway? Length of runway as X. So this is supposed to be X, because this is 74% of the length of runway, right? So length of runway is X. To make this more mathematically friendly, is 0.74x. So you can sub in your equation. So now, v square equals to u square plus 2as. I choose this formula because we have v, we have u, we have v, we have s. All of it. So just substitute in. U square is 0. Don't have to write it. 2, 4.2, your a is 4.2. S is 0.74x. So we are actually now finding for x. Okay. Then this is just algebra. 58 square divide by k. Oops. X is basically equals to 58 square over 6.216. 6.216 is basically this. Okay. The x, I just took out the x lah. Okay. You should get 541.18 meters. So if you round it off to two significant figure is 540 meter. And your answer is B. Yep. So as I've said before, you don't have to, write step by step like this. Okay. You can skip any step as long as you can get the answer. As long as you can get the correct answer. So make sure even though you skip steps, make sure you calculate it properly in your calculator. Doing it fast sometimes can cause you to write wrongly. And that's about it for question 6. Now moving on to question number 10. An object of mass 2 kg is traveling at a speed of 3 meters per second on a horizontal frictionless surface. This object collides head-on with a stationary object of mass 1 kg. The two objects stick together on impact. Okay, stick together on impact. That means this is an inelastic collision. It's good to know that. Okay. how much kinetic energy is lost on impact? Okay, to find out how much kinetic energy is lost, first of all, we need to know that in an inelastic collision, kinetic energy is not conserved. So it makes sense they're asking that how much kinetic energy is lost. So since it's not conserved, definitely your answer is not A. Cannot be. If it's elastic collision, yes, kinetic energy is conserved. So there's no loss. But since it's not conserved, there is kinetic energy loss. So how do we solve this? The thought process is you need to find what is your initial kinetic energy. Then you need to find what is your final kinetic energy. Ideally, okay, your final kinetic energy should be lesser than your initial kinetic energy, because final kinetic energy, there will be some energy that is probably lost through sound, lost through heat, etc. So ideally your final should be lesser than your initial, because initial is before collision, but final is after collision. So now after we find this, we find the change in kinetic energy, because the change, you are taking kinetic energy of the initial kinetic energy minus the final kinetic energy, right? So the difference gives you how much kinetic energy is lost on impact. Okay, now to start this, we first need to find out what is the final speed, because after it collides, we need to find the final speed. Why we need to find the final speed? Then only we can calculate our final kinetic energy. So in order to calculate our final speed, we use conservation of momentum. So initially it's just 2, 3 plus 1, 0, nothing. Then 2 plus 1, because they have stick together, both of the objects, v, which is what we're finding. So this is actually conservation of momentum formula. Okay, so we have 6 equals to 3v. This would say our final velocity, which is the velocity of the both object after impact, is 2 meters per second. So now we can calculate our initial and our final kinetic energy. Initial kinetic energy is 1 over 2, 3, 2, 2. 2 is the mass, sorry, 2, because 1 over 2 mv squared. 3 square, don't forget to square, plus 0, because the 1 kg object is at rest. So ideally you should get 1 over 2, 2, this is 9, you should get 9 joules. Final is 1 over 2, 2 plus 1. Why I put 2 plus 1? Because they have stick together. So now they are seen as one object. So 2 plus 1, and just now we calculate our final kinetic energy upon impact is 2 square. So 1 over 2, 3, 4 is 1, this is 2, you should get 6 joules. And it makes sense that your final kinetic energy is lesser than your initial. Oops, lesser than your initial as predicted. So now to calculate the loss in kinetic energy, basically you take your change in KE, which is 9 minus 6. And 9 minus 6 gives you 3 joules. And your answer is D. Yep. Okay. So first thing in this question is you need to identify what type of collision is this. If let's say this was an elastic collision, it did not stick together, you don't even have to calculate, your answer is straight away A, because if it's an elastic collision. If it's not, then yes, you have to calculate. Yeah. So you find your final speed first, then you use your kinetic energy formula to calculate your initial and your final kinetic energy, then calculate your loss in kinetic energy. So that's how you do question number 10. Next one, question number 14. Okay, a couple is applied to a tap as shown. What is the torque of the couple? Okay, we know our pivot. Okay, let's set clockwise as positive. So to know our torque, I think I can just do it here. Torque is basically force times distance. Okay, before even I do this, let me explain to you first. Clockwise I set as positive. This is going clockwise. How about this? Also going clockwise. Do not think this is going anti-clockwise, it's also going clockwise. Yeah. So, our torque of this couple would be FD, which is distance from the pivot, then another FD, which is 2FD. If you think like it's confusing to see two variables, just think of this as x and x. X plus x gives you 2x. So your answer is C. Okay, now it's question 18. Okay, this is an energy question. It says that total energy supplied to an electric motor is E. Energy Q is wasted, and the remaining energy does useful work. What is the efficiency of the motor? Efficiency of the motor. Okay, first of all, we need to know what is the efficiency from the energy efficiency formula. I believe this is not given in exam, so you need to know this formula, which is energy output over energy input. Because this formula you don't have to memorize, you have to just understand. To know the efficiency of something, just take the ratio of output over input. Then you know how much is it actually efficient. Okay. Now, energy output is basically E minus Q. Because you give in E, okay, but Q is wasted. Now, since Q is wasted, so how much will be actually used to do work? E minus Q. That's your energy output. Input is just E. So whereas this is a fraction, so what you can do is you can put E over E minus Q over E. You can split the fractions. This gives you 1 minus Q over E. Yeah, this is your answer. So your answer is, where is it? C. Please see properly, don't wrongly put D, okay? Yeah, so the main thing about this question is knowing this formula. Once you know this formula, you can do this. After you reach this point, always find a way to simplify it, because usually your answers will be in simplified form. Okay, then split your fractions, simplify them, you'll get 1 minus Q over E, and you'll get your answer. Yeah, so that's question 18. Okay, last one, question 20. A cylindrical steel rod with negligible weight has a diameter of 1.5 cm. Cylindrical steel rod. So that means its cross-sectional area is a circle. Okay. And a length of 5.2 cm. The rod is firmly attached at the top end. The rod is firmly attached to a machine at the other end that applies the constant force of 363 Newton to the rod. That means it's pulling. There's a machine here that's applying a constant force of 363 Newton. This causes the rod to extend to a length of 7.4 cm to have a minimum diameter of 0.60 cm in the position shown. Oh, here. Okay. What is the maximum stress acting on the steel rod when the length is 7.4 cm? Okay, so we know that stress has a formula of force per unit area. Right. Okay. Okay, the question specify here maximum stress. Maximum stress means minimum area. Then when they're asking you the stress at this particular region. So, first we need to find the area at that region, because the lower the area, that means you have a smaller diameter. So area equals to pi d square over 4, because it's a cylindrical rod, So it has the cross-sectional area of a circle. So you're using this. You can use pi r square also, but since they give diameter, I just really use the diameter formula. So pi 0.60, don't forget to convert to meters because it is in cm. Don't forget to square also, divided by 4, and you should get a value. Wait, let me put it in my calculator. Okay, I got 2.83, sorry. 83 times 10 to the power of negative 5 meters square. Okay. Now we can find our maximum stress, which is force, given was 363, right? Yeah. Divided by the area you found just now, which is 2.83 times 10 to the power of negative 5. Always remember to convert your units here, and you will get, oh, that's a very big value, 1.28 times 10 to the power of 7 Pascal. To 3 significant figure is 1.3 times 10 to the power of 7. Not 3, sorry, 2 significant figure. 1.3 times 10 to the power of 7 Pascal. And the answer is D. Okay. So here's the thing, they will not simply say maximum, minimum. Okay, there must be a reason. They say maximum, they want you to know what it means. They want to know whether you know what does maximum stress means. Whether can you relate it to the area or to the diameter. Maximum stress, by the relation of force per unit area, stress is inversely proportional to the area. So greater the stress, the lower your area. Lower area means lower diameter. Smaller diameter, I mean they want the stress at this part. And the maximum stress of the steel rod when the line is 7.4 cm is occurring at this part. Why is my arrow the other way around? This side, yeah. So you calculate your area, make sure to square, convert, very important, then just put in your formula, you will get your answer. Yep. So that's for part 1, the first part of the video. Okay, there's a few calculation questions that cover a few chapters: pressure, energy, we have kinematics, we have momentum, we have torque, we have efficiency, and we also have something about stress. So I hope this gives you an idea on like how your thought process should be when you look at these questions. So I'll see you in the next one. Thank you for watching. I really hope this helps, and bye bye. Make sure to stay hydrated.